Introduction and Fundamental Concept of Strength of Materials. Hello everyone. Welcome to this lecture on Strength of Materials, a fundamental concept in engineering mechanics. Today, we will explore the basic principles that govern the mechanical behavior of solid materials when subjected to various forces and loads. Whether you're new to the subject or looking to refresh your knowledge, this session will offer insights into the strength, stiffness, toughness, and stability of materials, all crucial for designing safe and efficient structures and machines. Let's dive right in. Introduction to Strength of Materials. As many of you are already familiar with, mechanics is the science of forces and motion. It's a field that has been deeply intertwined with human progress, dating back to the very beginning of our civilization. From ancient structures to modern-day engineering, mechanics plays a pivotal role in shaping the world around us. Now, when we talk about strength of materials, we are referring to a branch of applied mechanics that specifically focuses on the mechanical behavior of deformable solids under external loads. This includes various structural components such as beams, columns, plates, and shafts, key elements in everything from buildings to bridges and machines. In engineering, understanding how these materials behave under different conditions is essential to ensuring the safety and longevity of our designs. Key concepts and requirements. 1. Strength. The most basic requirement of any structural component is strength. This means that each and every component must be able to resist the forces it is subjected to during service. In simple terms, the material should not fail or break under normal working conditions. Whether you're designing a beam for a bridge or a shaft for a machine, ensuring adequate strength is fundamental. 2. Stiffness. Now, strength alone is not enough. The material must also possess adequate stiffness. Stiffness refers to the ability of a material to resist deformation, essentially how much it changes shape or size under a load. For example, if two components are meant to fit together perfectly, any excessive deformation could lead to a mismatch, causing functional problems. Interestingly, a material can be strong, but not necessarily stiff. This is why both properties must be considered during design. 3. Toughness. Next, some materials must withstand dynamic loads, forces that change rapidly or come in short bursts. For these situations, materials must have toughness, or the ability to absorb energy without damage. Toughness is essentially a balance between strength and stiffness, particularly under dynamic or impact loads. 4. Stability. Finally, we come to stability. Stability refers to a material or structure's ability to maintain its shape and equilibrium under load. Lack of stability can lead to sudden, catastrophic failure. For example, imagine a long column under compressive force. If it lacks stability, it may buckle and collapse even if the material is strong and stiff. Ensuring stability is key to avoiding these kinds of failures. Generalized procedure for analyzing strength of materials. In mechanics of solids, analyzing a system typically follows a structured approach. Let's break this down. Step 1. Setting up an idealized model. First, we begin by simplifying the system of interest. The real-world object, a machine, a beam, or any structural component, is isolated from its surroundings, and we create an idealized version of it. This simplification helps make the system easier to analyze while still capturing the essential physical behaviors. For example, instead of analyzing every microscopic detail, we might approximate the system using basic geometric shapes like rods or plates. Step 2. Analysis of forces. Next, we analyze the forces acting on the system. These could be external forces, such as gravity, wind, or loads applied to the structure, or internal forces, which resist these external forces. It's essential to understand how the forces are distributed throughout the system, and we apply equilibrium equations to ensure that the system remains stable under the applied loads. Step 3. Analysis of deformations. Now let's talk about deformations. Deformation occurs when external forces cause a material to change shape or size. This can be measured and observed, and it's often expressed in terms of strain, a measure of how much the material has deformed relative to its original shape. In most cases, we'll focus on elastic deformation, which means that the material returns to its original shape once the load is removed. Step 4. Application of laws. Lastly, we apply the laws that relate forces to deformations. These are known as constitutive equations. The most commonly used law in this context is Hooke's law, which describes the linear relationship between stress and strain in elastic materials. This law, along with other stress-strain relationships, helps us predict how materials will behave under different loading conditions. Part 4. Practical Applications and Conclusion. Understanding the strength of materials is crucial for solving real-world engineering problems. Whether you're designing a skyscraper, a vehicle, or a simple tool, these principles are your guide to ensuring safety, durability, and efficiency. By applying the concepts of strength, stiffness, toughness, and stability, engineers can design structures and machines that perform reliably under various conditions. The idealized models, force analysis, deformation analysis, and constitutive equations we've discussed provide a practical framework for approaching a wide range of engineering challenges. As we wrap up this lecture, I encourage you to think about how these principles apply to the structures and machines around you. Whether it's a bridge, a crane, or even the chair you're sitting on, these concepts are at work, ensuring that everything functions as expected. Thank you for joining me in today's lecture on the Introduction to Strength of Materials. I hope this session has given you a clear understanding of the fundamental concepts and how they relate to real-life engineering challenges. Be sure to explore further into each of these topics as they form the foundation for more advanced study in structural analysis, material science, and mechanical design. Basic Assumptions in Strength of Materials. Hello, students. Welcome to today's lecture on strength of materials. I'm excited to dive into a fundamental part of the subject that lays the groundwork for more complex discussions: the basic assumptions in strength of materials. These assumptions simplify real-world phenomena and allow us to apply mathematical models for structural analysis. They serve as the foundation upon which we build all our calculations and designs. So let's get started by understanding these key assumptions. Assumption 1, continuity of materials. The first assumption we make is that all materials are continuous. What does this mean? Under this assumption, we treat materials as if they are continuously distributed throughout the space they occupy. This idea is called the continuum hypothesis, where we assume the material has no voids, cracks, or gaps. Essentially, we treat the material as a smooth, unbroken substance that completely fills its volume. Diagram showing a steel bar and microscopic view of atoms. Take, for example, a steel bar. In reality, the bar is composed of billions of atoms, but for engineering purposes, we assume it behaves as one continuous block of steel. This allows us to use mathematical tools like calculus to analyze the bar's behavior under different conditions. We describe changes in variables like displacement, stress, or strain as continuous functions of position. Now, we know that real materials are not perfectly continuous. They have microscopic defects, but the assumption still holds for most engineering applications. Whether we're working with steel, wood, or concrete, treating the material as continuous gives us accurate enough results. Assumption 2, homogeneity of materials. The second assumption is that materials are homogeneous. In simple terms, this means that the material has identical properties at every point. No matter where you take a sample from, it will behave the same way. This assumption simplifies our analysis, as we don't need to study every small section of the material separately. Example of a homogeneous material, e.g. steel versus non-homogeneous like timber. In reality, most materials are not perfectly homogeneous. For instance, metals like steel can have small variations in composition, and materials like concrete or wood are obviously non-homogeneous. But for engineering purposes, the variations are often small enough that they don't affect the material's overall behavior. So the assumption of homogeneity allows us to simplify our calculations while still obtaining accurate predictions. Isotropy of materials. Next, we have the assumption of isotropy. A material is said to be isotropic if its properties, like strength or stiffness, are the same in all directions. This means that no matter which way we apply a force, the material will respond in the same manner. Diagram showing isotropic behavior of materials under different loads. Metals like steel and aluminum exhibit nearly isotropic behavior on a macroscopic scale, making this assumption quite useful in many engineering designs. However, on a microscopic level, some materials may behave differently. For example, single crystals of metals are anisotropic, but because we work with large quantities of randomly oriented crystals in real-world applications, the material averages out to behave isotropically. Keep in mind, though, that some materials, such as composites like carbon fiber, are anisotropic, meaning their strength depends on the load direction. But for most structural engineering applications, isotropy is a valid assumption. Assumption 4, absence of internal forces before loading. Finally, we assume that materials are free from internal forces before loading. In other words, we start with the material in a stable state with no internal stresses or forces unless an external load is applied. Seen examples of residual stress due to uneven cooling in metals or drying in timber. However, in real life, some materials can have internal forces even before loading. For example, metals that cool unevenly after casting or welding can develop internal residual stresses. Similarly, timber may have internal stresses as it dries. In most cases, these forces are small enough that we can safely ignore them, but when they are significant, we need to account for them to ensure accurate analysis. In summary, we've covered 4 key assumptions that form the basis of our analysis and strength of materials. 1. Continuity. We assume materials are continuous with no voids or cracks. 2. Homogeneity. We assume materials have identical properties at every point. 3. Isotropy. We assume materials behave the same way in all directions. 4. Absence of internal forces before loading. We assume materials are free from internal forces until an external load is applied. These assumptions help us simplify the complex behavior of real materials into something we can analyze mathematically and practically. They allow us to create models that, while idealized, give us accurate enough results for engineering design. Remember, while these assumptions are powerful, they are simplifications. As you move forward in your studies, you'll learn when and where these assumptions hold true and how to deal with situations where they don't. Thank you for your attention today, and I look forward to our next discussion. If you found this lecture helpful, don't forget to like, subscribe, and hit the notification bell to stay updated with more educational content. See you in the next lecture.